All right, we are recording. Let's get the back camera up. All right, so last time we were talking important things on timing and all this kind of lovely stuff, right? We talked about the different timings around a loop and what are the variables. By and large, these are not things you are going to be doing, with some rare exceptions, right? If you ever have to do like pull up or pull down resistors, things of that sort, this is going to imply a time cost and things of that sort. So you have to have some idea of what the R is you're going to do. So timing will put a value on what that pull up or pull down is. It'll put its requirements. You'll usually also have some type of an input current that it can handle and an output that it has to, be able to source, right? So we call that syncing and sourcing. So you'll get these sync and source currents, and you'll have to make sure that they stay within whatever the range, right? So you look up at the spec sheet and see, what does it need to be able to handle. Typically, your output, and then you'll get the input. Typically, currents are going to, since they, in our consideration, right, we're doing classic currents, flow from high to low, and so they come out of your inputs when it's high, and they go in when they're low, right? So that's your classic situation, sink and source. Now, when we're looking at any of those type of things, right, you have to make sure those sisters fit those. And like I said, that'll also put a time constraint. But otherwise, we don't typically worry about it. When you get into something large like an FPGA, it's too much for you to be able to do that on your own, so the machine does it. But you need to know what the machine does, because the machine will not always succeed. It's going to try really hard, but it is not always going to succeed. And if you understand where difficulties can happen, you can then massage your setup and let it try again. Right? This is actually one of the best things to ever learn from espresso, right? Because espresso, again, almost always works, and it's usually very fast. The problem being when it doesn't work, it's confused and it doesn't know how to get there. It can get there, but you have to kind of change the way the problem is slightly to have it start in a different position. Because if you've ever used a computer, sometimes it's a computer mapping thing where they're trying to find a root, right? There's lots of these different solvers. They will be able to find roots under certain conditions. There. Okay. Now, I did want to mention one more thing that I don't remember we did talk about, and it's worth mentioning. Most modern FPGA chips tend to be fairly large, right? Just imagine that. Usually it's too big to be allowed skew, so we talked about skew at the very end, right? If you consider that the signal has some propagation delay, so different systems are going to see the clock at different points, they're further along. If you really love physics, this means they're in different light codes. But one of the reasons why I was mentioning it and everything else is because to make you think and realize you are getting near relativistic scales and everything else. Now, what happens with these really large ones is we tend to break up the chip into regions that are handled by different clocks. So I want these clock regions on here. So if you look inside an FPGA, it doesn't just have one clock. And actually, it's going to have 20. Right? You're going to have, for each area, you will have phase shifts of 90 degrees, basically. Right? Two. So you will have all these shifted ones. Then you could have multiple different regions. Right? So you'll have 4 for each region, and then usually one global. And you might think the global is better, but it's got a longer skew. So those sub skews, right, should give you a shorter time to allow you to have bigger function to be able to do things. But you might need to trigger them. Typically, it's a 50% duty cycle, i.e., it's kind of down. So the different SKUs, right? Positive edges, zero negative edges, 80, right? But I could go halfway too, which gives me 270, use 3-pack overages. I have all these different SKUs to be able to find things. What's really important is if you realize this is under one clock and this is under another, what happens when I want to send a signal? Yeah, this becomes kind of complicated. Now it's really going to be hard to figure out what is my timing. So there are a variety of techniques to solve this. The safest is double buffering. I put a register on each side next to each other. In essence, if I'm trying to send the signal this way, because you should know what direction you're sending your signal, I dedicate a buffer. So what you just calculated at the end of the thing goes to the closest register on my side. And then all it needs to do for the next cycle is step across the line and hit the end. There's almost no time flight delays. There's almost no calculation. Well, there is no calculation price, it just goes through. Right? So when you start looking at all your timing issues, there's none of them here. So everything can be cobbled by SKU and you're still safe. And because all it does is walk across and checks into the hotel on the other side of the border, so to speak. Like, it's just literally, you're doing all day to deal with the annoyance that they don't use the exact same color. Okay? That will pretty much remove any errors you have. It's a near bulletproof design. So it's a very safe one to go. So double buffering is a big help if you have to breach these edges. So if your design gets too big that what you do, it can't. You split it into regions, force each region when they have to communicate to each other to go to a double buffer, which is just one register into another. And now you explicitly clock, and you use the clock in that region. We typically in our designs are going to use a global clock. And the reason why we're going to use a global clock, even though it's going to give much bigger amounts of skew, is our logic is so stupidly simple. Most of it's going to fit in a couple layers. There's nothing slow. It's probably going to be fairly small designs too, which means, guess what? Doesn't matter. Okay? It's not going. You're just not that cutting edge on anything you're doing in a regular class compared to what you're going to do in the industry. And for me to make something like that, I'm going to have so much complexity, you would miss the forest for the trees. Okay? So just think this, if you cannot ever schedule these two, take it into pieces, easy enough to do, set up clock signals inside each of the regions you get to deal with. So it forces it into those regions, double buffer between. So there'll be some signals that will go, on one side, the first register uses the first clock, the second register uses the second clock. Force them onto the border like that, it gets what you need. Does this make sense? So that's just kind of the last thing I want to on these clocking regions that's in here. All right, now we want to really kind of deal with interfacing and part of what I'm trying to do with interfacing here, I'm not as concerned with calculating pull up and pull down. This is more, I should probably even just call this my transition from hardware to what the heck's going on inside a Verilog system, Verilog. Next week, we are going into, you're going to be coding it and building it. So here is my first little bit of things on that. When you are done class and before next class, please go up to the help desk people and request to get a Nexus 4 board. Right? It'll be in a little plastic case, somewhere around like that. It's green on the cover, Nexus 4. If you did digital logic here, you use the basis boards. Now you're going up to the next level, the Nexus boards. This is a more advanced one. It's got more memory, more capabilities, but it's what we need. Right? We're going to be able to implement, processors and do all kinds of fun stuff. So all the advanced classes use the Nexus boards. So go up, there's tons of them. There's enough for like each of you to have three, but you don't need three. So just check one and they'll take your name and stuff. You have to return it by the end if they want your grade stuff. So don't go there. But just check it out, then you'll have the board available. We're going to do a lot of our stuff in software, but I highly recommend you don't just stick in simulation land. For this class's purposes, you should actually program it. In many cases, it's going to make very little difference. But there is a difference between simulations and implementations. Have you ever heard the definition of theory and practice? There's a joke. In theory, there is no difference between theory and practice. In practice, there is. Okay? When you start to go trying to implement your designs, things that were working well will all of a sudden run into problems because there are things you can write code for that you can't build. Things that you behave one way in simulation will change and will actually start behaving a different way. And that's because you didn't reach your simulation right. We're going to talk about, start getting into some of these issues. There are some things that you can write that have an implication you don't understand over time. And it will cause, right, when it's doing the simulation, it's going to assume certain kinds and behaviors based on your variable type, based on whether you did blocking or non-blocking assignments, all kinds of things like this. And if you gave it the wrong impression of what it was trying to deal with, it will simulate exactly as you say. But then when you go to build it and it builds something different, it will not build correctly. And you'll get tiny errors in it that it would have found if you had told it how to simulate correctly. So we're going to be, attempting to get you into kind of a standardized understanding way of what it's really trying to do. To do that, I kind of have to get, and particularly today, a little nitty-gritty on the language. So this is going to be kind of low level. What the heck is really meant here? What's implied by it? Introduce some new things. I'm going to be nitpicky on conventions. Particularly, this is my advanced one. Most internet sources state, even if they're from a university, they learned to code like 30 years ago, and they are still using stupid bad constructs for that. Okay, there are a few safe places, and I will try to direct you to them and create links and stuff to ones that actually do good code. And one of them is one that I highly encourage you to use, which is EDA Playground. Electronic Design Analysis, that's EDA. EDA Playground is actually implemented by a number of the people who are on the Verilog actual committee for IEEE that sets the standard, creates the language definitions and everything else. They're about as good of a source of what you're ever going to get on to do. There are several related websites that have teaching stuff, and their code is really stupid good. They also have free simulators that are some of the high-end simulators because they're the ones who write language things. The simulator companies want to keep them happy, so they give them access at least on a design, just kind of doing simple implementations on it, which they make freely available to people to demo the code because they want people to learn to code correctly. This is a wonderful thing for you because that means you can try some very high-end language compilers and everything else and see some of the differentiations. They all have their own little approaches. So getting used to some of these will really help you when you're moving on. So that's one I highly recommend. I'm going to talk as I go through here, and I give you some examples of language constructs you should never use, right, that are old. If you notice somebody using those language constructs in their example, run far, run fast. Okay? They have just proven they're an idiot. Okay? Don't listen to an idiot. There may be some nuggets of truth in there, but it's like digging through the garbage hoping you find a treasure. Okay? it's probably not worth it. Okay? All right, that's kind of just my initial warning and what I'm talking on these. So let's start out with the most basic construction we're going to deal with, which are modules. Module is it's think of it like a class. It's yeah. So it makes think of what a class does inside of C++. So everybody familiar with C, C++? I'm just presuming it's probably the most common language of entry, right? Does a class actually do anything? No, until you instantiate it, it doesn't do squat, right? So the whole point about them is they tell you how to build things, and then you can build many of them, and so it'll tell it how to do it if you ever bother to build it. But it's like the blueprints and the instruction manual all into one thing that should create something. The same thing with a module. You can define all the modules they want, and they will not build a single thing. They just say how to build it. Now, there are two major kind of divisions of the Verilog language. Really, I should probably say three, but I'm going to group them largely into, there's going to be the 90X ones, right, where X in here will be 5 or 1, right? So there's 1991 Verilog, there's 1995 Verilog, right? Do not ever write code in this. Okay? There's a reason. There are newer ones, and they are way better. There's the 2000 and X ones, which strangely again actually ended up having a 5 or a 1 in that because 2001 Verilog as the language and 2005. Technically, after 2005, Verilog ends. There's no Verilog after this. Because after this, it's no longer called Verilog, it's the same stupid language, but it's called System Verilog after that. All right, so that's kind of your third big group. That, if you think of this as kind of C, this is C++. Right? It just adds a whole bunch of useful things, a lot of it towards testing, but a bunch of things actually towards synthesis too. Unfortunately, people have moved on to system Verilog because they thought it was all for testing and implementation. And they're like, we don't need to test or validate, which is a terrifying concept anyway, that you write a code and doing serious testing and implementation of this. That should kind of tell you stupid statements like that, right? But anyway, they're tightly coupled. A lot of the great constructs are both. There are some really nice additions to the system there, but I will by and large treat them as one semi-connected thing. A lot of the language things have not implemented fully system Verilog. As a matter of fact, the tool you're using, which is a pretty standard one out there, only implemented a bunch of the system Verilog testing features about 4 to 6 years ago. So, yeah, and system Verilog is 2008. So, it took over a decade to get this implemented in to a decent extent, and there's still some things that finishing is what it is. The more you pay, the faster they implement. The high-end companies implemented in their things within 6 months to a year. The more common, cheaper ones, it's taken decades. That's where it is. Right? In that, here is C, here is C++. 1995 is the depth. Yeah, I really have no better thing to say about it. I did learn to code in it. It was actually even an earlier one, barely started in the 80s. But, that was like the devil's evil stepchild or something. What you want to call it. It was really horrible. But it was the only game, literally. There's no other programming language. that you could do hardware in the 80s. Right? In the 90s, Verilog tried to incorporate some new features that were starting to come in. This is when VHL got introduced, right? The 80s version of Verilog was so annoying because it was the first cut that the U.S. government determined it was too annoying to deal with, so they defined their own language, VHDL. And since they can't license it and make money off it, because they're the government, they made it an open source standard. It was mainly designed around the idea of documentation. So if you ever go to VHDL, it will take 5 times as long to say anything. But dang, it will build in documentation of exactly what you meant to say and what dialect you were speaking in. About half your time in VHDL is spent converting data types that are 100% compatible, but are different in the way you interpret them. Right? Sometimes they're even 100% compatible, they're just defined by a different standard, and you're explaining what standard is required on the different wires, even though they're not compatible. So VHDL, on the bright side, being very heavy document oriented, is going to catch almost any missed thoughts you have. It will catch any sloppy ideas. It takes longer to build and all kinds of other stuff, but that's why, right? Verilog is loosely typed as opposed to strongly typed, right? It's incorporated all of the updates that mattered, but it kept its more sleek form. So Verilog is a little bit faster, but modern Verilog, and this is partially why I'm pushing so heavily, something after 2000 has all of the good, safe features you should have, and system Verilog actually has more than VHDL. VHDL is trying to catch up to system Verilog because it added so many things to it that are really useful for good design and testing. Of these, anybody ever use VHDL? Then this is just to give you information. Right? VHDL is based on the language data, and Verilog is based on the language. So their syntax are based in those categories. Right? Now, since most people learn C, it is faster to learn Verilog than it is to learn VHDL. And it is a simpler language, so it's faster to learn. There is no dispute of this. Many tests have been done. It's faster to write and to learn in Verilog. Like I said, there are documentation things. Verilog is built based on synthesis, so there are some things you can do in Verilog you cannot do in VHDL. There are some things in VHDL you still cannot do in Verilog. But it's now based on the assumptions. Like VHDL wants you to document like crazy. Verilog has never had this much documentation features. You still don't have to tell them whether you're using standard logic or IEEE. If you think about it, yeah, there's really not a huge difference on this. There are some minor things on what standard you built them around, but that's, are you dealing with Europe's logic definitions that were based upon the IEEE? Some of the IECT stuff, or are you building it on, IEEE? They actually write out all these standards and then you have to convert between them. Right? So there are some annoyances on that. But it also is heavier documented than scope in that sense. What Verilog has is, since it's a design language, it goes slow. It has PMOS, NMOS, and CMOS actually transistors. It has those transistors, and you can actually build with the transistors inside of Verilog. You cannot do that inside of VHDL. It doesn't allow you to go to transistor level. Verilog is. Verilog is also parallel. It has constructs for fork and join and things of this sort, which is not really synthesizable, but it does allow you to do parallelization when you're simulating and things of that sort. You cannot do that in the HDL. Right? These are just trade-offs between each of them has a feature. What do you care? Right? There's been a lot of tests. If you learn either language, you can pick up the other pretty much with equal ease. So once you learn one, you can pick up. This is much like with children learning languages. If a child learns their native language well, they can almost always pick up another language well. If they don't learn their native language well, they almost always think they're picking up other languages because they just don't understand. So there's similar things inside here. I say all this because you'll see some people who are like crazy advocates one day. Um, I personally don't care. Use whichever one is easier. Right? I think there are easier ones to learn, but I think there is actually a place for VHDL and there is a place for Verilog. You learn one well, you can learn the other. Yep. And if you go to some places and they're a VHDL place, you're going to find that's the only language. And you're dumb if you use Verilog. And if you find a Verilog place, they're going to say the exact opposite. That's stupid, not with them, whatever they say, right? Because you can't argue with craziness, right? But just don't. And each one has their place. Um, we used to be a VHDL shop. They actually switched us to a Verilog place. And the reason I did is just faster. Right? It's not that one is better than the other, right? Um, you will find in academia it's about two-thirds VHDL. You will find in industry it's about two-thirds Verilog. Rough numbers, they vary place to place. Academia tends to be more VHDL because it came from the military, and guess who gives a lot of money to engineering academia? Yeah, DoD. So and when DoD was making their requirements and people were initially prepping out all their labs and things, DoD was requiring VHDL. So guess what they did? They went with VHDL. Most companies wanted to be able to hire people as there was needs in the 90s and early 2000s. Computers were growing like crazy. They needed to get people that were enough trained people, so they wanted people who had programming experience. And which language is easier to learn the first time? Verilog. So most corporate ones are Verilog because it was just easier to get somebody who was a C, C++ program and teach them the extra stuff you needed to. There you go. That's the reason why each side has their thing. You have been informed. Right? So anyway, we're going to continue with this one. I'm going to show you a first construct, why, what 95 looks like versus 2000, and give you a reason why you want to do it, suggesting, and it'll also be your fastest way to test when somebody's doing something stupid. Both of them are going to have modules, right? So we'll do the 9x here and the 2000x over here. Both of them, the first thing you'll do is put some name in, right? If I can spell correctly, name. And let's say, for instance, I'm going to have an input A and an output B. I don't really care. This is just a quick example to show you what's going on here. What we'll have here is A, B. Over here, we're going to actually have something that says like input, and maybe it's a wire, and maybe it's 3 to 0, A, and output, and maybe it's a range, whatever. Maybe again we're dealing with 3 to 0, B. Now, the information in here that I have in 2000X that we have put, right, this is your interface. Right? It tells you what the data type is, wire and the number of bits and stuff, and it tells you the direction of the port. These are called ports. Because a port is something like from C to N that's between two different groups that allows you to do it. These are ports. Right? That's why you got ports on your computer and everything else. So these are the port maps on this. It has all the information, one spot needing thing. You still have to specify that in 95. So the thing you do is they also have this extra stuff you do. Input A, output B. I specify my direction, but still the data type is, so I have to actually instantiate those variables. So therefore, I'm going to have to say wire 3 to 0 A and reg 3 to 0 B. So if you see this separate, they break it up. Inside the name, this be true inside of functions and all kinds of stuff. If you, yeah, right, right. There are surprisingly a huge number of people who still write code like this and stick it out there. And they tell you this is the way we do things. Okay? There are good places that will mention both formats and will say they are both legal, and then they'll try to push you towards the second one. That's being comprehensive. That's kind of what I'm doing right now. Don't think the fact that they list it means that they're advocating it. That's just acknowledging it exists. You should know if anything looks like this, don't do it. It's 9195. It's garbage. There are some significant differences, right? So there's more, and it would go to an end. It's still, they had to actually bring it in as a, yeah, it's grandfathered. Think of it like implicated. But there's so many people, and this is the sad thing, a lot of engineers, you still have a few people who graduated like I did in the 90s. When we were taught, that was the one we did. So I graduated early 90s, I started working actually, as a military contractor, so that was language I first started in. You know, and you went through it, but there was some ones that I had to deal with commercial stuff, so I used both languages. I had learned that syntax. It was the only game in town. You did what it said to do. Okay? But there were so many people who were trained, and after 10 years in the early 2000s, you had a lot of people who knew how to do it this way. So when they made the new language construct, they couldn't throw the old one out, or you wouldn't get people to do it. The sad thing is those people learning that that's why I can keep doing it, or you can learn a new syntax. So guess which one they did? They kept doing what they're doing. And then the internet pops out this great information source, and they're like, I can build my name. And so they put the Python code out there. But here's where the difference. You cannot do everything the same with both. How many people have done Verilog stuff with us, where you've written some modules and stuff like that? How do you instantiate? Okay, so this name right here has become like a data type if you want to. It's a thing you can build. So this is my type, so I say name. That's, this is like my class. So I'm saying, make me something using name. Right? That's what to go. Now I have to give an instance name, right? So, whatever. I'm just going to call it Fred because I'm sorry, I grew up with the Flintstones and Fred Flintstone, so you get it. Okay, so now I've got, name type and that is my particular instance name. We go open parentheses, and now I want to start hooking these up, right? I need to hook A and B. So I can say, for instance, dot A, and whatever my external variable I want to plug into that for A, and dot B, and whatever the external thing for B is. There we go. Okay? Now, if you think about this, you might look at this and say, oh, this is work. That's the dot A is an which is internal, which is external. Anybody ever use like classes or structs, things of that sort? Right? So dot A means the A in Fred. Right? That's what we're doing here. That's what the dot is. So you know that anything after the dot is into, you put in parentheses what you're passing to things. So that's the external. So if you know programming conventions, this is very easy. How to create way to interface these. Here's the neat thing. You know XA is going to A inside, right? And XB is going to B. There's no question about who's getting into where. Do they have to be done in this order? No, I could have done dot B, XB, dot A, XA. Order does not matter. There is another way, and it's still accepted here, but it can only be done in the old style. The old style doesn't have a choice, right? Where they say name and then Fred, right? Or maybe I shouldn't use Fred for this one. To make them distinct, I'm going to do Barney because Barney was the lesser of Freds. Right? It's always making mistakes, right? And now I just put comma B. You have to put them in order. Does this make sense? And you actually look at it and say, which one is quick, that's easy, it's short, less detail. You can do that if you never should. You should always do this. Here is why. The way in which this is passed, you might think whenever XA goes to A, XB goes to B. True. Most of it. But what if these XA and B are not the same size as A and B? This has 4 bits, this has 4 bits. What if XA has 7 bits? Now, what you would want is you would want the 4 lower bits of this to go to A and B to B, right? Doesn't do that. What it does is you have to find, you appended together a whole bunch of bits. And the first 4 bits are going to go to A, and the next 4 bits, which is still being pulled from XA, are going to start going into B. It will literally split across variable lines and all kinds of other stuff. Because how does it know where to split them? It doesn't. You just gave it an appended ordered list of bits. See, now you got to go in and make specific variable to prevent you from screwing up and doing it. You see how ugly this is? Right? Now, on top of that, imagine you even have the right types magically. And imagine you have a long list of these. Instead of just 2 variables, you're building a computer. So there's, 60 plus inputs into this particular. Are you going to recognize the functions? What if you add a couple bits because you went to a new version of that thing? That new version adds, right, because you have to upgrade it, but it's basically the same. It has a slightly different input interface. Now it's got a couple extra wires. They're not guaranteed to be in the same order. What do? And that is the right answer. You are going to cry because it's going to be virtually impossible to do this. I actually had a group about 20 some odd years ago when I was teaching back in California. The group for 3 weeks were trying to find a bug in their code. And they were working hard. And we were all looking at the stuff, trying to find it. We eventually found they had 2 of their variables switched. And those 2 variables they switched had very similar names, but they were different links, so it actually could split the variables across those 2 things when they came out, because they were doing this with them. Okay? When they discovered it, they flipped the 2 and everything started working perfectly, and they've been trying to hack through their code, fixing things. It was all a pork problem. Right? I mean, at that point, they were ready to kill themselves. Right? They were so unhappy, depressed, mad, right? Stuff like that. If you do this, you ask the new variables, whatever the new variable is, it doesn't have to be this to where it goes. You're done. There is no way to confuse if it's the wrong thing. This was meant to go here, so it truncates it correctly. No weird crossing or other stuff. Right? This is worth the price of admission right here. Right? This saves so much trouble. Right? Yeah. So,
just for personal thing, but could you not do dot A extend comma dot B extend any main line code?
you could. Yeah. Okay. So I could have done this in one long line of comments between them.
Yes.
I'm actually advocating you shouldn't. And here's why. You can do blank lines. How much does a blank line cost you in a digital space? You pay by the page, right? How readable is this? Okay, you may like the other way, but I argue too. Once you get, I think it's two things, nobody gives a shit. But in reality, you're not going to be doing two things in your design. You're going to have 30 things in your design. Right? A long list of 30 things, common separated with dots and parentheses. It is. So just get used to doing it this way. My reason is if you build up the pattern when you get there, it will be nicer. But it's really easy to just do these checks even when it's small. So I'm just advocating. There will be times that I'm just like, this is stupidly short, so I'm still here. I'll take the stupidly short advantage. But the vast majority of the time, I'm going to do this because it's readable. I can't tell you how many times I start with a shorter list. I'm like, oh, I need to put in an enable. Oh, darn, I need to put in something else. Right? The number of things I have to add later on, and I'm going to have to reformulate this. Plus, if you get used to this, when you're looking through, you've got a bunch of modules defined inside of one file. You can just rapidly go, oh, you see that pattern, and you jump to it. So, it's often said that this type of organization is the hobgoblin of small minds, to be that organized. And I am not one who, by and large, likes follow all the little rules. But when the rules save my butt, I feel it's important to follow the rules. Okay, and this is one of those things. It's not required, but dang, it has saved me at times. So I'm going to push that you try to do it, right? Whenever you're dealing with stuff like this, right? When you first learned math, they made you be really meticulous in how you formulated things and did them. And then over time, you got more casual, didn't you? Once you became comfortable with it. Okay? It's, that's fine. If you want to maintain it afterwards, yeah. But if you were, a little bit casual at the start, it sometimes becomes difficult to learn proof methods. So there are some weird things, like you don't learn where the dangers lie because you've learned how to do it comfortably. So I'm just suggesting, learn it this way. Once you become comfortable, you understand what's going on, find what works for you. It's just easier to start with good form and back off into comfortable than to start with comfortable form and add rigor later when you need it. Good? Okay. So this is one of my warning things. 95, you can see very bad, very dangerous, really easy to make mistakes. That's horrible things you don't want. 2001, that's exactly what you need. And is very safe. Now, you might say this is annoying to list. Like a device under test where I've got 30 things, I don't want to type those 30 things. Lo and behold, if we have something inside here and it was like dot A gets A type thing, maybe these things instead of A and B are really long, like, my input signal load or something like that. Right? So it could get to be a ridiculously long name. I can do things like dot A star, pick the same dumb name. So same wire name inside and outside. It's a shorthand. Star stands that, and I can do that with each of my pairs. Okay? And I say, what's the device on the text? I'm going to have the same variable name for everything. So instead of having to do dot A star, comma, dot B star, I can just do dot star, and it says hook up all the internal wires to their name. Now, since I have this lovely notation, I can mix things. So imagine I had a long list of 30 things, and I wanted to list dot A to X A, but everything else I wanted to hook up to their own names. This one does matter. You just got to tell it the exceptions before you tell it now hook up everything else to the same name, because otherwise we would have tried to hook A up to its own name, and then you can change things, stuff like that. So you have to give the exceptions first. But again, it'll all be shorthand stuff. Does this make sense? So again, more magical, wonderful things you can do only with 2000 and beyond. Okay, what are the data types? So this is interface. Okay. Yeah, so what's the difference? What's the idea behind these? So here's the fun thing, right? What would your first thought be when you hear something's a wire and something's a register? You would think registers, maybe, we've got registers. Yeah, it does. Okay. It's trying to get to us, what's a register do? It holds its value, right? This is all on the programming end. A wire does not hold its value. It has to be continuously driven. A register, you can assign it a value and it will hold it until you change it again. Right? So it allows you to set it at certain points. This is totally for how you write this up inside of your code areas. It also affects kind of a little bit the timing of how certain things happen. This is why some things can go to some things and others to others and not, right? A wire always needs somebody to tell it what's going on. Imagine I had a wire in my hand. If I tapped one end to a 9 volt and held it there, the other end is at 9 volts, right? If I lift it off, is it still at 9 volts? It has to be continuously driven to get something, right? Now it's floating. Right? With a register, in essence, there's no implied permanent memory to be built. But in software, so remember I said there's going to be a difference between simulation and building? When it builds the same dumb thing it does. Okay? This is all about how you set the values. And therefore, certain things will be easier to describe than certain ones, so we use them to build things. But if you think about it for a sec, a ridge, what it's going to do is then hold it. Okay? So I can just say, give it 9 volts, because sometimes it's easier to say, give it 9 volts, and I mean keep on going. So if you want to write things as a computer program, you say, A equals such and such, B equals such and such, C is A plus B, right? And you expected between program lines that it held its value. If that was a wire, it wouldn't. It would have just been, that instant, right? But what you were saying wasn't, I'm just going boop at that instance. You're saying at this moment, make it have this, and keep that value. So the next time I tell you to change it. Right? It's just a shorthand. So you're not meaning something physically different. It's a way of expressing things. Does that make sense? Right? That's the whole reason behind these. Because of that, since wedges can be assigned once and it quote unquote holds it, you can do this in a program. I just wrote that upside down. See, I am dyslexic, so I have the ability to write things in different directions and still think I'm saying something else. This is in a programming area. You're going to write this as procedural. So, anybody know if the procedural pops on? Initial is one of them. Anybody know the other one? Common one? Always. All right. Anybody know the difference between these two?
Initial only happens at the beginning. It's the initial. Always is keep doing this until.
Yeah, so the difference is what we call persistence. Right? Initial and always both start at the beginning. After initial finishes, it ceases to be. Right? Always will continue on, and if you change anything on a sensitivity list, it'll go again. It's not that it's an implied for loop or something of that sort. It is a permanent existing thing. Whereas initial, only just does something at the beginning and then it disappears. Which one can you build?
You can put it in niche flow.
How? Can you build something that ceases to exist at a certain point?
As we explained.
Yeah, so it's floating, yeah. That'd be a cool thing to it, right? You still have stuff, right? So always is synthesizable. Initial is used for test benches. Because what you're saying is the person comes in, flips these switches and walks off. Right? That's kind of the differentiation. So initial should only be used for test benches. Right? Some people extend this slightly and use initial also to set values. So for instance, like I might use an initial block to specify that I am downloading code from my computer and putting it in ROM or something of that sort for variable access later on. Right? So it might be part of that boot process in some sense because it disappears later on. There are actual ways to do this properly with a bootloader, which I would recommend. That's a little bit safer. But if all you're doing is something kind of quick and dirty and it's going to be loaded once and it's going to be at home and it's never going to happen again, then it's not necessarily too bad. It's a shorthand that just understand the ups and downs of the shorthand. So that's some of the differentiation. There is actually a third type for this, but you will probably not use it, which is called fork join. I mean, fork join is that parallel stuff that's not synthesizable. It does have persistence. And it's often used for forcing things to happen simultaneously. So it can just be used, what if I want some type of a system that's going to respond to your thing, so it doesn't need to be built, but it's going to be some other rest of the universe component that responds to fork join is a nice way to do that. So, but you will not do that in this class or in education. That's really just special stuff when you go out there. So that's just for completeness to mention that thing there. Now, these types were available the entire time period. When you go to System Verilog, they add in some specializations here. Always comb, always latch, and always flip-flop. Now, under the original one, the ways you would tell the difference was the sensitivity list. So if I wanted a combinational circuit, which System Verilog uses this, I would just say always at star. This is also a difference between Verilog and VHDL. This at star notation is actually available in Verilog and not available in VHDL. Now, my own experience on this, at star is a lovely thing. What it means is inside your module, the left side is what you're assigning to of an equation, right? The right side is what you're taking to calculate to figure out what the left side. So if the right side stuff changes, you need to recalculate, don't you? Right? So everything on the right side should be in the sensitivity list. Does that make sense? Okay, well, here's the fun thing. In VHDL, you don't have to do that. You can actually pick a subset of those. Because you might be trying to imply some hardware that, it holds all the values when it comes in, and it only updates those based on the sensitivity list. Right? You almost never need that. Right? But they actually put it explicitly. You add another line. You better remember to add the things on the right-hand side to the sensitivity list. This cost myself, my grad students about 13 years ago, really a good week trying to find this. We had a long sensitivity list. This was only a project that was going to find this thing. So you had to be really crazy fit. And we couldn't find it. Out of this long list, one variable had been missed. And it took us a while to hunt it down, and that variable wouldn't update. It was all done in HDL, so it was kind of in the Air Force. But it was annoying as once we found it, put it in sensitivity, it just instantly everything stopped. Right? Just annoying. If we had it stopped, it automatically takes everything off that puts it in this. Right? That is what you need combination. The only way you can have things not in the sensitivity list is anything in the sensitivity list goes into memory and get held. Right? So now with memory, you put the right hand side in there and the sensitivity list controls when it goes in. Right? So anyway, right, that's combinational does this. The other disadvantage is latches also do this. You want to use latches. Flip-flops also do things. So when do we do a latch versus a flip-flop? Flip-flops are edge triggered.
So latches is basically.
Exactly. So you only use latch when you want to do an asynchronous design. However, the most common thing to happen to generate a latch is the following. If A, B equals C. If I have something like this, this will generate a latch. This is actually an error. You did not mean this. This is totally legal, but it's bad. Okay? Because think of what this is going to build. An if statement builds what? Mux, exactly. All right? So I've got my mux. This mux has a 0 and a 1. All right? What is my control? This says build a mux. This is my control. So A is here. So when A is 1, I do what's here. Right? If, then do this. So this means B, well, that's got to be the output. C has to be the input. What goes into 0? See, I haven't specified. Now, it looks completely specified when I wrote this if statement, but you left off of the condition. This is why I say you have to think about what is it going to be. So implicitly, what should it do?
It should put the
We want to hold B. Right? That's what it's going to assume you mean, right? Don't change B, but that means you have to do this. You just fed it back. We just talked about, that's how we build these circuits, we just feed it. So you just built a leech by feeding them. Was this properly, was it time? Does it have critical races? You just did this and you didn't know down the kid. You didn't know you did this. See the danger? So under the starter, there's no way it can, did it mean to know this? It's a legitimate thing to do. So it'll really do it, and it will tell you in the messages, latch. It'll give you some warning. If you see warning, latch, any type of latch mentioned inside, then this is what it is somewhere. You have an asynchronous piece that you didn't know about that just got shoved in there. However, you almost never mean this. Okay? If you always comb, you don't need the at star at all because it anything it has to. There's no anything. So it'll automatically do that for you. And if you ever generate a latch, it'll throw an error. It won't let you move on. It'll tell you the line that it threw the error. So you can immediately go find exactly what it was going to go. And you go, oh God, you forgot the else. And then you can solve the problem and move on. You should always do the always underscore versions, because if you miss to build memory feedback and you're building an asynchronous circuit, then put the latch. It won't do anything weird. It goes, okay, you want to build a latch, it won't try to avoid it. It will often try to avoid it by doing anything it can instead of that. It's only when it doesn't know how to avoid it, it will build the latch. But then it's not going to get back to what you intended. If you do the latch, it goes, oh, they intend a latch. Let's change it, just follow. And so that's the safe one to do. So you should only ever do these, right? And in this class, you're building on the FPGA, so latches are not, they should never really be because FPGAs are timed anyway. So you're only ever going to be using comb and flip-flop. When you do flip-flop, it has to be edge triggered. So you still need the sign here, and you'll have either pos edge, and then whatever the variable is, or neg edge, and the variable. Right? So whether you're using call edge fragments A or B, after that it would be call edge A, close parentheses. And that's telling you you're going to trigger all the positive edge of this. Does this make sense? And so this becomes a really important issue. You still have to do these with a flip flop because it has to know what is your clock input. You'll put the clock inputs here, and if you have any other important things like an asynchronous clear or something of that sort of reset to it, you also have to put that in this list. Because those are also important. Oh, you've got an asynchronous clear or an asynchronous stat, something of that sort. It needs to know that to hook them up. So that also goes in the sensitivity list. But now sensitivity lists do what they really should do. You are specifying controls that are global and not part of the regular code. It's telling you when the sample went to reset, that sort of. These are special condition areas. That's how they're treated in most things. Like in most circuits, do we draw the clock? No. We just, when it's a memory unit, you know it's on the clock, and you just can't use. This allows you, to be able to, in essence, put that information somewhere. All right. Do we feel good with the difference between these types? All right. How do I set? So this is only for registers. How do I set wires? Yes. So can I, have a wire driven by a module? Actually, it doesn't matter what the output is. It can be, a wire can be driven by any, because once you've assigned, if the output was a reg, right, the input may be periodic, but the output is constant. There's always an output to a reg. There's always an output to a wire. So a wire can read from a wire edge, but a reg cannot read from a wire because the wire may have a value, may not have a value. Right? Now, as a driver, now can I sample a wire as an input to a reg? Of course I can, because now I've told you when to read it. Right? So I can't just stick a wire, just fix it to a reg. I can't assign it. Right? I can't have a reg take an output of something unless the output is a reg. So if the output is a wire, I can't just put a reg to that because when do I sample? Right? What's my update next? So this is where those differentiations come. And you have to be very careful on them. Right? Because that's where they happen. Generally speaking, if you're going to do it in code, it's a reg. If there's a statement called a sign, where I can say something like, whatever, C equals D or something, right? That's solid, right? You cannot change this later. I have said for all time, C is D, or I could say C is equal to D ampersand E. I've now built an AND gate and made C the output. You built it, it stays forever. That's an assigned statement. I can take it from a module. A module will drive its outputs. Great, it's driven. Right? Any wire has to be driven. Good? So if you attempt to misuse these, use a reg as a wire, things like that, it's going to throw an error for you. And it will tell you, like if I try to put a reg and feed it into a wire and I don't, because the one, the whole statement thing, I can't interchange them. I can't put a reg in an assigned statement. So if C was defined as a reg, it would be a problem because that says hook them up, but I never told you when to read it. A reg wants to read something and hold. Does that make sense? So what we'll do at that point is say, not a net. C is not a net. It doesn't tell you it's not a wire. Anybody take advanced programming? Hear about polymorphism? Okay, then it's not going to help you a huge amount. There's an underlying, there is this idea called polymorphism, where you can build a base class that has a lot of the kind of features, it's a whole bunch of shared stuff, and then you can polymorph it into other forms, and in those other forms you can add the special extras you want to it. Right? So it's kind of like if you have to build 20 things that are 90% similar, you don't want to repeat it that many times, right? And maybe you'll have to change it later on, and you don't have to go back and change it in, a whole bunch of different places. So you build a base underlying thing, and then you polymorph it, right? So it's kind of like a base class that you're going to build on. Does that make sense? Right? So the wire, there's a whole bunch of things that are like a wire. Right, that aren't just wires. So they made this thing a net, because the wires can go all kinds of different places, like a net can. And they said, we'll build this base thing, and we'll polymorph it into a wire. They also polymorph it into a couple other different types that are out there. So these are all net types. So just as a note, right, there are also buff if 0, right, buff if 1, not if 0, right? Not if 1, right? Things like this. This is a buffer, looks like this, and this is this is buff if, technically this is a buffer if it's a 1, right? It's control wire to it. This is a tri-state gate. Right? And it's saying if my control wire is a 1, act like a wire. It's a buffer, it just has a slight delay. Buffer 0 just has the negated version of the control wire for the tri-state gate. The only difference between a buff and a not is the not has the negated outputs. So otherwise, exactly the same thing. It's a control, it's a tri-state gate, either with inversion or non-inversion. So you can think of, bucket 0 and bucket 1, PMOS and NMOS. Right? One A responds to a 1, responds to a 0. Right? And then I either have an order on the output. But there's all kinds of other ones too. This is some of them. Other ones you might care about, there is what's called supply, either 0 or 1. These ones between that. So let's say, for instance, I wanted to have a power input that's now I could say reg A and just set A equals to 1 and leave it. Is that make A a reg and then set that in an initial, I just set A equals 1 and I never change it. Is that because all this so it is content, you can use it. But you ever notice sometimes some things can overpower other things? So there are strength of signals. That is power. That is true. But supply one means I hooked it up to the main power supply. There is no signal stronger than a supply 0 or a supply 1. I said this is the power supply, this is the ground, right? It will overpower everything. If you send a 1 to a 0, you get this kind of indeterminate state. Well, look at the 0 and getting a strong. We do this all the time. When we did our little diode logic, right? This one, if I put a 1 here, it gets close to a 1 over here. Right? So in order to handle something, if I want to add the 0 back in, I have to hook a resistor to ground. Right? This is weak, really weak, right? Because that resistor kind of blocks it. So if I apply a 1 here, even though it's not the greatest, it dropped from 5 volts to 5.3, or sorry, 4.3. This resistor can't fight it, the resistor dissipates it. It's very weak. But if I'm not doing anything, the resistor pulls it down to zero. Adding a resistor to ground is a weak zero. What if you didn't have the resistor there? Well, that's a stronger resistor than you can supply. That's supply zero. So by these variables, you're actually specifying how you're hooking it up. You should only use supply zero and supply one if you really need to hook it to power. Because this is a very, very unprotected power signal, right? It's strong, it's great in that sense, and if you meant it, you meant it, right? But it's also dangerous. Your chance for shocks and damaging things also. Just know what you go with. Make sense? There are some items that are here. You'll see. I just mentioned these because you might run into them. Um, anybody have any idea what that would be? See, most people are going to try to make a word out of a small thing. It's an abbreviation: wired and wired. So I can actually make a wired out an AND gate. So consider this lovely little beastie right here with the diodes, right? What if I take a diode coming in and I make this A and I make this a wired version of A? I diode. Now I could take this, right, a wired version. Well, what if I had two of these different things? Here's B and a wired version of B. Can I hook A to B? That, and then, and what's going to happen in this particular case? And
One's on, it's one of them.
it's still on, whichever one's on is. So implicitly, what does that wire connection do when I solder them together? It doesn't work, right? This is called a wired or. So I have to declare what it's going to. So I would declare the combined circuit over here, right? Let's say this is whatever, this was A and B coming in, and then this is C. I would declare C of type wired or. And then I can say assign C equals A, assign C equals B. Now that sounds like it's contradictory, but I told it that C is required or. So if I assign multiple wires to it, I told it it's going to behave like this. So it just turns it into an OR gate. But it doesn't have to build the OR gate because I'm going to put this diode connection. So it knows, oh, you meant to put that diode buffering in here that prevents the shorts, and I do a wired version of this gate. But literally, that wire acts like an OR gate. But the only way it worked is I hook the diode, or I can do a similar type of a thing with transistors, things of that sort. I can do, if you flip the direction of those transistors, you get an AND gate. It's called an AND gate. So if you wanted to do one of those gates, you have a way to do it. You will do this like maybe once in an oddball problem, probably only in school. But you might actually see this in a circuit where there's this weird connection and you're like, what the hell's going on? It actually, there is a symbol for this in electronics. This is an OR gate, so we draw an OR gate over the top of it. Centered on the line. That, so if you ever see that in a circuit where there's that OR gate kind of drawn over, like in shadow over the center, it's things aren't coming through the normal inputs. It's just drawn over. That means it's a wired and that the electronics on it, because I put some other circuits before it, in this case, I put diodes. It will behave like an OR when you hook them together and you don't actually have to put any fancy logic. You can just do it. Right? And you tried, you did this, right? So you know it works that way. And that's what they're saying. It's just a way, how can I specify it in language? I have to have a way of saying it. This is how you say it in Verilog.
How what advantage does it give us? Because is this smaller than an OR gate? Is this less power? I mean, diamonds, we're losing if still in 0.7.
You will almost never do this. Okay? This was a very common thing done in the 70s and 80s. It has to be carried out. It does have some weird uses. What happens if I'm building a bus and somebody hooks the bus up and I want to protect it from having some bad behavior? So on the coupling of these between buses, if somebody does something weird and doesn't tap in and their tap is done badly into it, then, how is it going to behave? So it's more in these type of situations you're going to deal with it because it's often done with transistors where either one side of the collector or the emitter is left. So that's common for building a bus because it won't short. They can't short. So since it's short, that gives you an advantage. Only if you're dealing with bus dynamics like that. Now, what do you do if somebody's hooking multiple of these and some problem happens in my underlying circuit or things of that sort? I just want to build a connection and I can daisy chain as many of these as I want. Well, the wired version actually makes it very easy to do that. And it enforces them. It would be really limited if we would ever want to do that. That's why I'm stretching. So the lead has to give you a way of saying it. Okay? And literally, I mention this because I've seen it a few times in this space. I've actually gone to legacy books and seen the screen of the collection. You need to know what the heck it means. You might convert it into a better new design. What you should know it means, you're just like, what the heck is going on? So I'm trying to cover to you the ideas behind it and where language comes from, because at the end of an advanced class, you ought to be able to look at pretty much any printed circuit board that comes out there and read the dumb thing. Right? You ought to be able to look at diagrams and understand it. You ought to look at code and nothing throws you for a loop. Right? So that's just pretty much what I'm trying to get across here. Right? So you understand. These are all just versions of wires, right? This is just saying wand and war. There's an equivalent one, which is try, right? So there'll be there's also a data type called try and try or, all one word squeezed together. Try and try or are identical to wand and war, right? Wired and wired or. They are identical. The reason why they try is try suggests there is a V state that is permissible, right? And technically with these, we're trying to say really just want zero. You don't. Will it support a Z state? Yes. Wired in and wired over, you don't apply voltage anyway. Got a handle it, you'll get the X or the Z's, right? But that's what you're trying to. So wired in and wired for, I'm telling you, you're trying to build one of these. Right? It's design intent. Try and try for. I'm trying to build a buffer to build a bus, say, for instance. But if some idiot hooks another thing directly in, I want protection to make sure this doesn't destroy them, that I don't get a short. What happens if two people use? Right? You're technically getting short of the bus, maybe, depending on how you hook it. Maybe you have pull-ups, what would you do? Right? So this tells you how I want to do it. Both of you talk. Do I want them to preserve the one? Do I want to force it to a zero? What do you do? And I might make whoever's talking or controlling this, right, my bus controller, respond based on those type of inputs. So I want a known function, right? These ones allow me to get a known function when two people try to talk to things. You don't get shorts, you get a replicable behavior, right? Like I said, it's a special case. But if you have to deal with that, you need to know what to do. Are we good? Okay, we've got into data types. There's a few more. We'll continue on this next time when it happens. But from now on, we're going to be dealing with a lot of language constructs and things. So make sure you get those boards from the support team.